I'm not the first person to ask the question posed in the title of this video. It was first suggested by some mathematicians back in the 70s, and they were considering whether the inner core could suffer from some rotational instability due to what we would now call the Dzhanibekov effect. They had lots of maths in those days, but didn't have the computers that we have, and they couldn't really visualize how it would all work. The idea next appears in the literature in 2002 when two Romanian material scientists are working out whether the inner core can maintain a permanent dipole, despite the fact that it's so hot. They thought it could, but it's not a popular idea. And if the inner core is going to play any part in geomagnetic reversals, it's an essential element. So we'll discuss that later in the video. Now, let's take a look at how the magnetic field is actually generated. Yes. At the centre of the Earth, we have the inner core. It's solid, made of iron, and it's very hot, about 5,000 degrees. It's under extreme pressure and so is very dense, a little bit denser than lead, but not as dense as uranium or gold. Iron is not ferromagnetic above 730 degrees, so in the conventional scheme of things, it plays no part in generating the Earth's field. There is no great bar magnet at the centre of the Earth which is responsible for the field. It's created by some other mechanism entirely. At the centre of the inner core, we have the innermost inner core. It's also solid, but it's thought to be crystalline. Surrounding the inner core, we have the outer core. This is similar in composition to the inner core. It's not under so much pressure as the inner core, and so is liquid. Rapid rotation forces the liquid outer core into long column-shaped flow structures aligned with the rotation axis. These are called Taylor columns. As these columns move and shear the electrically conducting fluid, they generate electric currents, and those currents sustain the Earth's magnetic field, roughly parallel to the axis of rotation. The Earth's rotation controls the direction of the field, but not its polarity. This is controlled by the handedness of the columns. The flow pattern is effectively a bistable state. The columns can settle into a right-handed or left-handed orientation. The magnetic field remains in a stable state for many thousands of years, and it's not clear how this happens without some sort of biasing. We're familiar with the Earth's magnetic field when it looks like this, but sometimes it looks like this. Every now and then it reverses. Let's take a look at some of the characteristics of these reversals. They are not regular. The field can remain in one configuration for long periods at a time. For example, it has stayed in its current state for about 780,000 years. That's quite a long time. But during the Cretaceous, there was a period of 37 million years where it stayed the same as it is today. During a reversal, the field tends to fragment into many parts which then reassemble when the new configuration establishes itself. But despite all this chaos, there is a small portion of the field that never goes away and tracks a course from pole to pole. It looks for all the world like there is something making a simple rotation at the Earth's centre. During reversals from normal to reverse polarity, the pole always takes the same track every time. Conversely, when the reversal is from reverse to normal polarity, it's a different track every time. The conventional understanding of magnetic reversals relies on a very large and very complex numerical model of fluid flow in the outer core. It's an enormous computational challenge, far beyond what even our most powerful supercomputers can simulate at Earth-like conditions. To make the model run at all, the input parameters have to be shifted to values that are many orders of magnitude away from those in the real Earth. When you do that, the model can't produce a reversal. The main dipole breaks down into a patchwork of smaller magnetic structures, and a new dipole eventually emerges with the opposite polarity. But crucially, it does not show a coherent dipole migrating smoothly from one pole to the other. The reversal in the model is a collapse and regrowth, not a physical flip. The model, if tweaked to produce a reversal, shows the field decaying and reappearing. It does not show a persistent dipole rotating as is observed in the field. I really can't say for sure. I'm not party to conversations between academics, but I believe that the shortcomings of this model are widely recognised. The parameter tweaking is one obvious reason why this may be the case. I personally find it difficult to believe that such a large fluid body will change configuration in such a major way without some external stimulus. Call me old-fashioned, but water doesn't flow uphill. In my opinion, the reversals are caused by a simple rotation of the inner core. The inner core has enough of a dipole to bias the field produced by the outer core. When the inner core dipole lines up with the axis of rotation, then the fluid motion in the outer core acts to amplify its dipole. The mechanism behind this flipping is a Dzhanibekov effect, and so let's take a look at that. If you have ever thrown a tennis racket in the air, you may have noticed something odd. It doesn't simply spin smoothly, it does a half flip before you catch it again. There's no way to avoid this. It's pure Newtonian mechanics, first described by Leonard Euler. The effect is sometimes called the tennis racket theorem, but these days it's better known as the Dzhanibekov effect, after the cosmonaut who observed it in weightlessness. On Earth, gravity hides the effect. It masks the motion, damps it, and makes the flip hard to see. So when Dzhanibekov filmed it in orbit, it wasn't a new discovery, but it was a revelation. It showed that all those differential equations Euler worked out really do describe something real and physical. So how does this apply to the Earth's inner core? In a later video, I'll present evidence that the inner core grows episodically. Its outer surface grows very slowly, but deep inside, in what we might call the innermost inner core, pressure changes can cause small spasmodic shifts in density, perhaps crystallization events. These may happen quite often, but just occasionally they could push the inner core into a very slightly triaxial shape, with the rotation axis lying close to the unstable axis. Under these conditions, a flip will eventually occur. Now, this is a body rotating once per day, and here I am suggesting that flips separated by thousands of years are related. But the triaxiality is tiny, and the angle between the rotation axis and the unstable axis is tiny too. Under these circumstances, the time between flips becomes extremely long. I'll demonstrate this using my model in a later video, so for now, I respectfully ask you to suspend your disbelief. There's one more piece of the story that needs the same suspension, the magnetic dipole of the inner core, and that's what we'll explore next. So much of the argument in favour of a simple rotation causing geomagnetic reversals revolves around whether it's possible that the inner core can maintain a permanent dipole. Conventionally, this is deemed impossible because iron heated above its Curie point loses its ferromagnetism long before it melts. Under these circumstances, the inner core cannot maintain a dipole and so is completely passive in generating the magnetic field. There is some research from Romanian material scientists asserting on theoretical grounds that iron can be ferromagnetic under these conditions, and these scientists did indeed suggest the simple rotation idea. Pressure-induced ferromagnetism is known from lithium and calcium, which are not normally ferromagnetic. Hydrogen on Jupiter is a metal and may be ferromagnetic. There is no certainty that the inner core can maintain a dipole, but the idea must be entertained. Current theories on reversals bend over backwards to avoid assuming the inner core dipole. If we start with the counterintuitive assumption that it does so much of what happens in the Earth's core becomes a lot easier to explain. Its predicted behavior under this assumption is so close to reality it constitutes compelling circumstantial evidence that the dipole exists. This image was generated by AI, so it's for illustrative purposes only. It shows how north to south reversals all follow a similar path, and it's a different path to that followed by south to north reversals. This is also a characteristic of Dzhanibekov oscillations. My modelling code, which will feature in the next video, uses Euler's rigid body equations to model the motion of the inner core. I set it up with a very high level of triaxiality so its effect can be seen without a long wait. You will see this same characteristic. Downswings follow one path and upswings the other. When it comes to evidence of what's happening at depth in the Earth, we are a bit short on evidence, but I think this is strongly suggestive that what we have is a result of the Dzhanibekov effect. Okay, it's time for a quick recap of the whole proposition. The inner core lies at the heart of the Earth. It's a weak permanent magnet, so has a small dipole. That's the bit you see migrating from pole to pole during a reversal. It grows in fits and starts, so occasionally it gets a little bit skew-whiff and can be subject to a Dzhanibekov style flip. While it's rotating in step with the rest of the Earth, the inner core dipole serves to keep the geodynamo dipole in place and acts as a stabilizing anchor for the rotation of the Taylor columns. When a reversal begins, that stabilizing influence is lost, and during the period of reversal, the geodynamo dipole descends into chaos. Order is only restored when the reversal is complete and the inner core is once again rotating in step with the rest of the Earth. I think all this is good physics, right? It all hangs together. There are no holes in it. And it may not be how the Earth works, right? But anyone who says that it cannot work this way, well, the onus is on them to show that it can't. I've spent the last 3 or 4 years working on this, and I've had a great time. I love a bit of programming, so it was great fun to do. So thank you for watching, and maybe you'll watch subsequent videos.